In this problem, we're examining the relationship between the algebraic expression of a linear function and the graph of the linear function. And we're trying to make some connections between the behavior of the equations and the shape of the lines. So this exercise is actually a good way just to kind of feel your way through it. It's a matching problem, so you can start with any line or any equation and see if you can see which one it matches with. And generally, when you have a matching problem like this, a good strategy would be to find the things that don't look like the other things and see if you can see how some unique behavior on one side matches up with some unique behavior on the other side. So take a minute, you can pause this video, see what you think, and I'll come back and talk about a couple of things about this. Okay, so when you're going through this, you may notice a couple of things about the equations. For example, over here, this last equation, q of x, is the only one that doesn't have a plus something, like a y-intercept value given. And that just means that the y-intercept of that should be 0. So if there's no number there, that means that 0 is there. And the only line over here that goes through the vertical axis at 0 is line E. So that's enough to determine that that line must be line E. The other kind of unique behavior that I'm seeing here is that line A on the right is the only one of these lines that's actually falling as you go left to right. So we would say that's a decreasing function. All the rest of the lines are increasing functions. And we know from our study of lines that a line being decreasing corresponds to its slope being negative. And so that's why on the left-hand side, you only see one linear equation that has a negative slope. It matches up with the one line on the right that's decreasing left to right. So that means we know that this line, that the p of x line is really line A. If you look at the remaining lines, B, C, and D, you'll see that C and D have very similar shape. And if you notice this question at the end, that might lead you to realize that C and D are actually parallel. So parallel means that they're never going to intersect, which means from the part that we're seeing, as they go left to right, the lines are not getting any closer together or further apart. So we have no expectation that they will ever meet. The way that's reflected in the equations on the left side is two lines are parallel if they have the same slope. And that makes sense. If they're going up at the same rate, then if they don't start off being in the same spot, they're never going to meet. So I know these two guys, F and G, are C and D, and I can just look at the y-intercepts to decide which one's which. So D has a y-intercept of 0, -3, and F has a y-intercept, should have a y-intercept of 0, 1, and if you look at the graphs, that's what's happening there. And so that leaves us with just h of x as the only one that's unresolved, so that must be B. But another thing you could have noticed about B in the first place is that h of x has the biggest slope of any of these. That slope 3 is the furthest slope away from 0 of any of the slopes. And so that means that we expect that the graph of h of x should be the steepest of these lines. So a large positive number slope would be a left to right increasing line that's very steep. And if you had a really negative slope, like a -3 or -5, you would have a super steep slope of a decreasing line. So the further the slope is from 0, the steeper the line is going to be. And then the last thing I wanted to point out is this condition about perpendicular lines that may seem like a weird particular thing to focus on, but this actually does come up in calculus. It's important because when we're measuring direction or distance between things, often the perpendicular direction comes into play. For example, if you were standing in the middle of a field and you want to walk to a road that's nearby, you wouldn't just walk sort of randomly towards the road. You would, if you wanted to have the shortest distance, you would walk in a direction that's exactly perpendicular to the road. I know that sounds like a dumb particular example, but that's just to illustrate that when you're measuring distances, which we do a lot in calculus, the perpendicular direction is relevant. So we think that A and E are perpendicular here because it looks like where A and E meet, that seems to form a right angle, and it certainly is not true for any of the other pairs of lines. Now, I want to point out that when the lines were parallel, that meant that well, it didn't mean, but when the two lines that were parallel had the same slope. And so even if I didn't have the picture on the right, I would have known that the graphs of f and g would be parallel lines because they have the same slope. There's a similar condition for perpendicular lines that's not as well known or not as obvious, and that is that perpendicular lines have slopes that are negative reciprocals of each other. Now, let me just say what that means. It makes more sense if we write our slopes as fractions. So the first slope for A, I'll write as negative 2 over 1, and the slope for E is 1 over 2. And so these are negatives of each other. I think that makes sense. So one has to be positive and one has to be negative, and that makes sense that if one's going up, the other one has to be coming down. But the reciprocal part is the same idea of reciprocal that we talked about in solving equations with fractions. It's just flipping the fraction over. So we'll say that the slopes, when you see two slopes that are negative reciprocals of each other, those two lines definitely are going to intersect at a 90-degree angle. So more obscure than parallel lines, but useful.